Good morning, students. Let us continue our chapter 13, and today's topic is electromagnetic induction. Till now, in chapter 12, in electricity, we discussed that if we want that current should flow in a circuit, then we have to apply a battery in the circuit. So, can it possible that without application of battery, current can flow through the circuit? Yes, it is also possible. So, this is possible by electromagnetic induction phenomena. Let us discuss about this phenomena in today's lecture. Michael Faraday told us that the motion of a magnet with respect to a coil or a change in the magnetic field induce a potential difference in the coil and produces induced current. This is known as electromagnetic induction. So let us understand this phenomena with the help of this activity 13.8 given in your NCERT book. We'll take a coil and connect a galvanometer with this coil. What is a galvanometer? Galvanometer is a very sensitive device which detects the flow of current in the circuit and also tells us the direction of current flowing in the circuit. In ammeter we discuss that ammeter tells us the amount of current flowing through the circuit, but ammeter don't give us the direction of current. But galvanometer tells us the direction of current as well as the amount of current passing through the circuit. So in this circuit we have connected this galvanometer. Now we have taken a bar magnet and we are moving this bar magnet towards this coil. And let us consider this north pole of this bar magnet is moving towards the coil. As it is moving, we see a deflection produced in this galvanometer. When this needle shows in the middle at 0, it means current is not passing through the circuit. But if this shows a deflection in any direction, it means current is passing through the circuit. So we observe that when we moved this north pole of this bar magnet towards the coil, this deflection was paused in right direction. Now we take this bar magnet away from this coil. Then again we see a deflection in this galvanometer but in opposite direction, say in left side. Now again what we'll do? We take this south pole on this side and north on this side. And now we are moving the south pole of bar magnet towards the coil. Again we see a deflection in the galvanometer in opposite direction. And if we take this south pole of bar magnet away from the coil, again we see a deflection in galvanometer and in opposite to the prior case. So as we are moving this magnet towards or away from the coil, we see deflection in the galvanometer, which means that a current is flowing through the circuit. From where this current have come? No battery is applied here. It means this current is induced, or we can say produced in the circuit due to motion of this bar magnet. Is it necessary to move this bar magnet only? Can't we move this coil? Yes, we can move this coil also. We can keep this magnet stationary and we can move this coil towards or away from the bar magnet. And again we see a deflection produced in the galvanometer. So what we can conclude? we can conclude that either we move this coil or we move this magnet, then a current is induced in the circuit. It means there should be a relative motion between coil and magnet. There will be current induced in the circuit. More speed of the movement, more is the amount of current produced in the circuit. Now, if we move both the coil as well as this magnet in same direction and with same speed, will there be induction of current? No. If we are moving both in same direction with same speed, now we can say that there is no relative motion, there is no change in distance between the coil and magnet, then no current is induced in the circuit. So this was the observations of this activity. Now what is the reason, what is the cause behind the production of current, induction of current? When a magnet is moved towards or away from the coil, more and more magnetic field lines pass through the coil. Because as we know, this bar magnet have magnetic field of it, and as it is coming near or going far, the magnetic field lines which is passing through the coil is changing, and due to change in these magnetic field lines, the potential difference is induced in the current in the circuit, and amount of current also produced in the circuit. So let us read. The magnetic field around the coil changes. The change in magnetic field induces potential difference across the end of the coil, and as the coil is connected to the galvanometer, it forms a closed circuit. So induced potential difference makes the current to flow through the circuit. The presence of this current in the circuit is shown by the deflection of galvanometer. Now let us discuss activity 13.9. Because it's not necessary that always we should have a magnet and a coil. We can do the same phenomena without the magnet with the help of another coil. So in activity 13.9, actually it is an important activity and it comes usually in your CBSE exam. And in this activity, we'll take two coil 1 and coil 2. Coil 1 is having large number of turns and coil 2 is having small number of turns. This is known as primary coil and this is known as secondary coil. Now, a battery is connected with coil 1, but the galvanometer is connected with coil 2. Now, what we'll do? When we switch on the circuit, when we close the circuit, then what we'll observe? There is momentary deflection in galvanometer. Suppose to this side, right side. And after that it comes to 0. Now when we switch off the circuit or when we open the key, then again we see a momentary deflection in this galvanometer, but in opposite direction, that is towards left side. Again when we close the circuit, again there is deflection in galvanometer, and again if we open the circuit, then still there is deflection in galvanometer but in opposite direction. So why it is happening? Thus deflection in galvanometer is showing the production of current in the circuit. Why the current is induced in the circuit? Let us discuss the reason behind this. So, cause of induced current in coil 2 due to coil 1. Actually what happened, that when we switch on the circuit, initially before switching on the circuit, the current in coil 1 was in the circuit was 0, and when we switch on circuit, the current from 0 increases to a maximum value. And as current start increasing, as we discussed in earlier lectures, more the amount of current, more is magnetic field associated with the conductor. So as current is increasing from 0 to maximum value, magnetic field is also increasing from 0 to maximum value. And as magnetic field is changing, it means magnetic field lines are also changing. Means in this case, magnetic field lines are increasing. And as magnetic field lines are increasing associated with this coil 1, it also encounter with coil 2, and due to change in magnetic field around this coil 2, the induced current is produced in the circuit, and this galvanometer shows deflection. But why momentary deflection? Why it comes back to 0? Because after reaching to the maximum value, the current becomes steady. It becomes constant. And as current becomes constant, magnetic field lines also becomes constant, and no change in these magnetic field lines now. And as no change, therefore the current induced is 0 in this circuit, and it shows 0 value. Now, when we switched off the circuit, open the key, initially the current was maximum, but when the key was opened, the current goes from maximum to 0 value. And as current decreasing, so magnetic field lines also decreases from maximum to 0 value. And now as due to decrease, again change in magnetic field lines, so the magnetic field lines near this coil 2 is again decreasing, means changing. So again current is induced in the circuit, and galvanometer shows a deflection in opposite direction. This was the reason. So on the basis of these activities, we can define electromagnetic induction as the phenomena of producing induced current in a closed circuit due to changing magnetic field is called electromagnetic induction. Now, what are methods of inducing current due to changing magnetic field? As we discussed two activities, and in both activities we discussed different methods. So on the basis of these two methods, we can write there are two methods of the induction of current. Number one, motion of a magnet with respect to a coil produces induced current. And number two, that change in magnetic field in current carrying coil produces induced current in another coil. Now, in practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. It means we can move any of the two things, either coil or the magnet. The main motive of us is to change the magnetic field lines. There should be relative motion, and it is convenient in most situations to move the coil in a magnetic field, and we are using this concept in the working of our generator. Now, very important, the induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. So question arises that when the induced current will be maximum, or what should be the position of the coil and the magnet. So these should be mutually perpendicular. Factors on which induced current depends. Number 1, the number of turns in a coil. Number 2, the strength of the magnet. And number 3, the speed with which the magnet moves towards the coil. So more the number of turns, more will be the induced current in the circuit. We can say these are directly proportional. More strong the magnet we take, more will be the induced current. And if the magnet moves very quickly, means more the speed of the magnet, large will be the induced current in the closed coil. Now, rule to find direction of induced current by changing magnetic field. That in which direction the induced current will be there if we are changing magnetic field. So it is given by Fleming's right hand rule. So don't get confused with Fleming's left hand rule. That is giving something else. So in this case, if the thumb, forefinger and middle finger, thumb, forefinger and middle finger of the right hand is held perpendicular to each other such that the thumb points in the direction of motion of the conductor, the forefinger points in the direction of magnetic field, then the middle finger shows the direction of induced current. So always remember. Applications of electromagnetic induction. Electromagnetic induction has found many applications such as generators. As I discussed, generators are based on electromagnetic induction. Inductors and transformers. You will read about these things in higher classes. A device used to produce electric energy at the expense of mechanical energy is called electric generator. We use mechanical energy and produce electrical energy in electric generators. And the principle of electric generator is electromagnetic induction. Now in text question, explain different ways to induce current in a coil. So different way, number 1, by moving a bar magnet towards or away from the coil, the magnetic field changes around the coil because of a relative motion between coil and magnet, so the current is induced in the coil. Number 2, if the given coil is placed near another current carrying coil or a conductor and the amount of current is changed in the conductor, then the current is induced in the coil due to change in magnetic field. So this is based on activity 13.8. This is based on activity 13.9. Now, if we are not changing the amount of current but we are moving the coil, if the given coil is moved relative to another current carrying coil or a conductor, then the current is induced in the coil due to change in magnetic field. So we have to prepare this chapter. Till now we have completed our physics syllabus, and the rest of the syllabus comes under deleted part. We'll cover that also, but till then revise this and prepare.